quite related, Lydia is going to be telling us about some of the interoperability work that the CHIUW group has been doing. CHIUW interoperability with other languages. So.
These newer laptops do not have.
The dongle is as big as a laptop.
Cool. Okay. Hi. My name is Lydia Duncan, and I'm a member of the CHIUW team at Cray. And today I'm going to be talking to you about our recent improvements to CHIUW as a library. So, as you are no doubt aware, production code is frequently large, the product of numerous hours of effort, and rewriting such code is a pain and easily able to waste your time with good reason. However, maintaining old code, especially in older languages, carries a burden of its own. New hires might not be as familiar with the language, and new hardware might require updates to maintain or improve performance, especially if a lot of explicit tuning was done to begin with. CHIUW has the benefit of being a modern language while allowing a greater degree of control for performance when necessary, but it can be difficult to justify writing apps in a language that is arguably still trying to gain popularity, and a big risk to port a whole app over. Having a strong interoperability story would make this easier. Developers could implement in CHIUW the aspects of their program that would benefit from CHIUW features, and integrate that with other pre-existing or new code. CHIUW did have prototypical support for library compilation, but it wasn't really where it needed to be for it to be used in this manner. And as you're going to hear in our talks later today, the improvements made to it in the past year have already enabled the integration of CHIUW code into a product, though much work remains on the feature. I'm going to tell you about these improvements, but first I need to give a brief introduction to the feature. So, code that is intended for use from outside of the library is declared with the export keyword. At present, this is only applicable to concrete functions, so module-level variables and type definitions, etc. are future work, and as such, can't really be used in the declaration of the functions themselves. And in the example code that I'm going to use throughout this talk, I'm going to be referring to a simplified sample library, which compares the behavior of 3 strategies for computing pi using the Monte Carlo simulation. These 3 strategies are fairly simple, but one of them is running over the computation serially, one is exercising CHIUW's task parallel features, and the other is exercising CHIUW's data parallel features. I'm not going to show you the code itself, but it will be available after the talk online. The story here being that our user is wanting to compare these strategies against their own implementation in Python, Fortran, and C. With that background, anything that's worrying people before I get started? Cool. So we're going to talk about Python interoperability first. Python, obviously, is a very popular language, and part of why it is popular is due to its productivity. It's very easy to write Python code. But when you think of performance of Python, you're typically thinking of libraries that have been written in C under the covers. And C isn't productive like Python is. It takes a lot more effort to write, and there's a lot more to think about when doing so. Contrast that to CHIUW. If the library in question were written in CHIUW, Python developers would probably feel more at home. This isn't a new idea that I'm saying. Simon Lund developed a solution called HiChapel back in 2014, and we've maintained it until recently. But it involved a package separate from the CHIUW compiler, and in order for it to work, it required the user to decorate their code in a very particular way. This package implemented its argument translation very much on its own, and due to limited resources, thus left HiChapel rather brittle and prone to failures if certain assumptions were not met. For this reason, when we revisited it, we decided to look into other solutions. So, you may or may not be familiar with Python. It's a tool that is provided to Python users to allow them to interoperate with C code. And it's had a lot more attention put into its portability and stability over the years. And we found that the support code that you need to write in order to utilize Python would easily utilize information we already knew during compilation so that we could generate these support files. By doing so, we greatly reduced the effort required of the user to little more than they would need for a Python module. By generating the support files for the CHIUW compiler, we can also utilize information that isn't relevant to C programmers, even though we're still generating C code to interface with Python. In this case, we can utilize argument default values, increasing the utility of exported functions, and making the process more natural to Chapel and Python users. So, this looks pretty nice, right? Pretty simple and straightforward. And I can go into the various little support files that have had to be written and had to be generated, but a lot of the point is that it's just fairly simple now. So, going through a little bit, we've also done something similar for C interoperability, but due to its very nature, a lot more of the work is visible to the end user, as opposed to Python where it gets very much brushed under the rug. C interoperability was a bit of a chore. It involved guessing a lot of information or digging in places where only language developers should go, and then writing it out by hand. As you can imagine, this was pretty dull and error-prone. Take a look at this header file that we've written off to the right-hand side. Sure, you could guess roughly what the syntax would be right for translating the serial version from the Chapel code to the C code. And yeah, it probably makes sense that you'd want to have that pound include there, but you wouldn't have thought about it until it bit you, and you maybe would have used the wrong integer type to begin with. And what even is that Chapel init Monte Carlo pi thing? That's an underlying support function that we need to know to make sure that our variables are initialized properly, but the user's not going to guess that they should include that. It's really not fair for them to even ask that of them. And then, once the user figured that out, you had to compile the thing, which involved using the right pound includes, or dash i's and dash l's, which is pretty extensive, and you don't want to have to write that out. We do have a tool down here at the bottom to determine how to use those, which of those flags are necessary, but it operates based on the environment variables you have set, like Chapel tasks. It has no knowledge of an individual program's additional requirements. So if you compiled with additional libraries, or if your code had a require statement that did so, or say in the worst case scenario, you were relying on another library that did so, you'd get a compiler error, and then you'd have to go and find what you needed to include, even though you specified it when compiling the library in the first place. All of this information was known to the Chapel compiler, or easily determined based on information it already had. So, as with Python, and in part prompted by having to do it a lot for Python, we decided to start generating a lot of what we could. We now always generate a header file for you, and can generate a helper make file to make it a lot easier to compile with these different flags that are needed. And the make file that we've generated includes this the information for you that was a lot harder to track down. In contrast to Python and C, we didn't have any support for Fortran prior to this effort. And while Fortran has a strong user base in the HPC community, we got interested because of the oceanographer, as Brad said, and also because Fortran interoperability has a lot stronger support for arrays, and we were looking into how to support Chapel's various complex array types in interoperability. It's got a nice interface with C that we can use to build onto this. But first we had to work with Fortran itself. So, the basics are very similar to the other two languages. We generated some translations so that the code can be used relatively naturally in Fortran without extensive effort on the user's part. The compilation command is a little bit more involved due to the Fortran version being disconnected from Chapel. For our C versions, we know the C compiler because we're already using it ourselves, but the user hasn't had to use Fortran with Chapel before. So, the Fortran compiler is needed to, getting ahead of myself. First you compile your Chapel library using the library Fortran flag. This will generate the library file itself as well as an interface module for Fortran. The user will then run that interface module through the Fortran compiler to get a module description file, which can then be used with their own code and all of the pieces that they have already to finally generate this executable. And Yeah, that's a little bit more work than we'd like people to have to do. We're hoping to take much of this effort and put it into a helper make file as well, so that the Fortran user is similarly benefiting from the under the covers work that Python and C encounter. Diving into arrays a little bit more, since I just mentioned it. Prior to this effort, exported functions couldn't have array arguments or return types. The old Python solution had started supporting just one particular type of arrays, 1D arrays of reals, but it didn't really have a way to support them more generally. And C interoperability treated even arrays with an explicit domain and element type as generic, and thus couldn't export functions with them. Being able to interoperate with arrays is important, but it's tricky due to how powerful CHIUW arrays are. For now, we perform a pretty natural translation between CHIUW 1D arrays and Python or Fortran 1D arrays. Due to C's handling of pointers and array size not being associated with the array itself, we require C users to provide us a little bit extra information before allowing it to get passed into CHIUW. Of course, CHIUW doesn't just support 1D arrays, as I've alluded to earlier, and we'd really like a way to expose our more complicated array types. For now, we've allowed them to be returned and accepted opaquely, so C and Python users can't modify the contents of the array itself, but they can obtain them, and they can call other CHIUW functions with them. This is intended as a temporary solution, and we hope to transition these array types to native support, especially in Fortran and Python. Fortran's array interoperability C will be pretty useful in providing this support. So, what's next for the interoperability features? We've got a number of things on the docket. As I mentioned earlier, we've only support 1D arrays naturally. We'd like to extend this to 2-dimensional, 3-dimensional, etc., as well as getting the more native support for arrays that are more complicated, like block and cyclet. We'd also like to support MultiLocal libraries. So today, when you are compiling your library code, we only really allow it for single locale programs. I'm going to go into a little bit more detail in a minute. But obviously, as a language that is focusing on distribution and working in a parallel and expansive manner, we want to be supporting these multi-locale compiles. We'd also like to look into, as Brad mentioned earlier, supporting C++ and also compiling your CHIUW library and then using it again from CHIUW. There's some barriers in the way of doing this, but we do think it's possible. So, multi-locale libraries. A little bit of background here. As I mentioned, they're not supported. Part of the reason for this is that in our multi-locale setting, we've got a launcher, and it didn't really adjust for the fact that it wasn't given an executable. So it would try and distribute that library as if it had a main function, which it didn't. CHIUW also expects to control how the program is distributed, which is a lot trickier when you're getting called from another language. So we had, for over the course of the year, we developed a mock-up our intended strategy, and users can and have implemented it themselves, but as I've alluded to, it's a lot of work and you don't want to have to do that. We've started adding this automatic support, but there's still some kinks to work out. We expect there to be a basic version in 1.20. So, how does multi-locale regular execution work? Well, first you compile your program, and it generates for you the launcher wrapper, which is named the same as the original library. It also generates a separate executable for the actual work, the meat of the program itself. Then the user on the login node in this case executes the wrapper, which will launch the reel itself onto the various locales that are necessary, which will then start communicating with each other and performing the work that you want it to do. We'd like multi-locale libraries to feel natural. Like non-library multi-locale execution, users shouldn't have to worry about how to launch their program, at least no more than is necessary. And whether or not the user's library is executing on, or the user's program is executing on the computer, not login node, shouldn't be important. We'd also like to support similar behavior for function calls, argument types, etc. to single locale. It shouldn't be that like you're walking over a big wall in order to switch between these two modes. It should feel as naturally transitioned as going between a single locale or a multi-locale executable. That said, we do expect to have the user supply an locales argument to specify the number of locales that should be required in this program. So we're going to generate the standalone binary to be launched. Its existence should really be a black box to the user. It's going to be used by the library itself, but the user themselves is not going to be responsible for how that interaction happens. And the library's interface is going to communicate to this binary using a socket. So the binary itself, executing on the compute nodes, will wait for function calls from the socket and then execute them. And we are using 0MQ to communicate this. There were some extensions that weren't present in 119, but they are on the master today. So, user code is going to link to this library, and which, as I've said, launches the binary on initialization. And in place of the functions that would have been the actual work on a single locale, they're going to have these basic wrappers that communicate to the library. So in our example program here, it tells you, hey, I want you to run this particular function, here are the arguments, and then it's going to wait for the return value if there is one. We'd also like to implement a protobuf module for serialization, because it's costly to send each of the arguments across the wire individually. So bundling them all together is just natural. This would also potentially, by having a protobuf implementation in place, we could allow the users to sidestep our argument type restrictions that are in place now because we can't export types. If they wanted to send a particular class instance, they could serialize the instance themselves and then send it across the wire to unpack on the other side if they wanted to get ahead of us. In addition to this, protobuf is a pretty well-known and widely used package, so having an implementation for it in Chapel is beneficial on its own merits. So, short term on that, we already have split the user source code into a library and executable subcomponents. We already have implemented the communication between both sides. It currently supports C-string arguments and most other primitives, with the exception of complex numbers, and we still need to extend it to support arrays. We're also looking into supporting Chapel strings naturally. And beyond that, once we get that all shuffled up together, we'd like to start working on the serialization strategy. And that's it. If you want to learn more about this feature, we have a tech note describing all of the currently supported features. We intend to create a primer to demonstrate the generated libraries in the next release cycle. And of course, you can ask us questions on our mailing list, Gitter channel, Stack Overflow, etc. Yeah, questions?
I should know the answer to, but is it really the case that, I thought we supported the multidimensional arrays in the Fortran interop. Is that not the case?
I don't believe we've actually done explicit work for that.
Okay.
Related question.
Yeah.
You do start to support multidimensional.
And shoot, I can't quite hear you.
Yeah.
When you do start to support multidimensional arrays, how would you handle any reshaping of arrays if it's needed?
So supporting them naturally in, you mean like a reshaping call from C or Python or Fortran?
Yeah.
We probably want to be exporting like the functions that would do that in a way so that the user would have to interact with them so that we update the appropriate information, because it's going to be like, you're going to be able to access it and see the portions of it as expected, but reshape is a function call, and the implementation for how to do that would still be controlled by Chapel, I would expect. Does that sound?
But I guess what I'm getting to more is that Fortran carries the meta information about the array shape around. I don't think others do.
Yeah, so I think you're right. I think in something, if you had, for example, created your own multidimensional array in C, even though C doesn't really have multidimensional arrays, then somehow you need to convey that meta information to us. With the Fortran work, kind of the question I was asking Lydia was, we've already kind of started using the, I can't remember the name of it, do you? It's like ISO files that are provided by Fortran that allow you to get out that meta information from within C.
ISO Fortran binding.h.
Thank you, all right. And so we were already going into that and sort of querying the Fortran array for that information and translating into the best we have in CHIUW. So for a case like Fortran to CHIUW, we should just be able to maintain the multidimensional characteristics. And I think for NumPy arrays, the hope is to do the same thing.
Yeah,
And so C is kind of the outlier because it doesn't really have good multidimensional arrays, I would say.
but we'd probably, so the intention with this ISO Fortran binding file is that we'd be able to use that sort of setup that it has. And Fortran, so in this link that I have over here to the place where the Fortran interoperability is defined, it's got specifications, like this is for Fortrans interoperating with C. So in C, you're able to see those fields that exist. You're able to see information about the shape of it and that sort of thing. So we'd be leaning pretty heavily on that as ways of conveying this sort of information so that it wouldn't be lost when going to C.
So since John asked about it, I went and checked. We actually do support multidimensional Fortran arrays.
Huh,
Yeah.
I missed that.
Yeah, so like if you had an m by n array in Fortran today, it would end up being an m by n array in CHIUW as well. And I think, if I remember correctly, and I don't know for sure that I do, but I think there's something really strange about that ISO header where you actually can't get the native indices of the Fortran array if you used anything other than the default one-based indices. Like I think that information is for some reason lost in that C interface. And so if you, for example, had a Fortran array that went from -100 to 100, I think in CHIUW that would end up being 1 to 200 or whatever it is, which is a little bit unfortunate. But as best we could tell, the ISO, that information was lost in that ISO struct, which seems shameful.
And I wanted to add, it might not have been clear, there are actually two totally different array interoperation strategies. One of them was the opaque array, one for distributed arrays that Lydia was talking about. And when she answered your question, I think she was talking about that one. So, like, maybe not, but that's what I understood. But the other one uses this idea like the ISO Fortran binding, or in C there's a little struct that we can use that we made up, right? That has things like these strides per dimension. So it depends greatly on which one of those is being used. But if it's got the struct or either the one we made up or the Fortran binding one, then you can handle lots of different kinds of reshaping just by changing what's in that struct, and what goes across the interoperation boundary.
Yeah, I believe in the Fortran case, what we do specifically is, like, we've used that struct in, I think, both cases, but then once it's gotten to the, like, Fortran call level, we have an unwrapper that makes it a native Fortran array. And then takes a native Fortran array and does the same thing to make it into a CHIUW array.
Right. And I would say philosophically, our hope is that if there's sort of a one-to-one correspondence between the external languages array type and ours, we'd like to kind of convey that through as naturally as possible, like in Fortran. And in cases where there isn't a correspondence, where our distributed arrays are the most obvious example, then we would have this opaque strategy. And then I think the challenging question is kind of if you're somewhere in between those, like C, for example, you've got a multidimensional array in CHIUW, you want to pass it out to C. Is it always opaque, or do you have some way of kind of linearizing it for C and making the C programmer aware of that? I think that's where a lot of our design, we wrestle with the most, probably.